Welcome to HKN TechX 2023 and our session on reducing the cost of ownership through reliable electric drive components, sponsored by our friends at John Deere. I'm Nancy Ostin. I'm the director of IEEE at Acapanu, or HKN. HKN is the honor society of IEEE with over 200,000 members. HKN inducts top students from around the world and bestows the honor of membership on professionals who distinguish themselves based on scholarship, character, and attitude. TechX is an opportunity to bring together industry, like our friends here at John Deere, thought leaders, academia, and IEEE technical societies to the IEEE members and IEEE-HKN members regarding the impact on their careers, research, society, and your communities. Thanks for joining us today. And I have the great pleasure of introducing today's speaker for this session, Skylar Hagen. Skylar is an electric drive engineer for John Deere Construction and Forestry Division in Dubuque, Iowa. In his role, he's responsible for design, selection, and integration for electric machines and other high voltage components into the new John Deere electrified construction equipment, as well as providing guidance for electric machine laboratory testing for product validation and verification purposes. Wow, electrified big trucks. How awesome. Take it away, Skylar.
Thank you for the great introduction, Nancy. And as Nancy mentioned, my primary role is with high voltage electric drives components, and we'll get a little bit into what we do at John Deere Construction and Forestry and how my work involves component reliability and particularly electric machines. So I'll start off by just introducing a little bit about myself quickly and a little bit about John Deere. So I did my undergrad in physics and master's and PhD in electrical engineering at UW-Madison through the WEMPEC program. During that time, I attended many IEEE conferences and participated in quite a few publications. So that was a great part of my educational experience. During grad school, I interned at John Deere one summer and then joined construction and forestry in Dubuque, Iowa full-time in January of 2020. So John Deere, as you may be aware, is a worldwide company. We've got many locations in the US and Europe and all over the world, really. You may be most familiar with John Deere's green machinery that you see out in farm fields and people's lawns. We've got our tractors, harvesting equipment, and all sorts of agricultural equipment. But what you might not have been quite as aware of is the side of John Deere's business that deals with construction and forestry equipment. John Deere is actually the world's leading producer of forestry equipment and is also one of the leading producers of construction equipment throughout the world. So my role at John Deere specifically is involving the construction equipment. So in addition to things like bulldozers and loaders, we make things like skid steers, excavators, articulated dump trucks, quite a wide range of products. And many of those products are built right here in Iowa, where I work in Dubuque and also Davenport and other locations. So we have one goal that really supports the work that I'm presenting here, of 20 or more electric and hybrid electric vehicles by 2026. This is a very aggressive goal and definitely ensures that we stay busy in the electric drives area here at John Deere. So just to talk a little bit about some of the electric drives construction products that I've been involved in. We've, for several years now, been producing the 644 wheel loader. That's a diesel electric hybrid. Not only does this eliminate the need for a mechanical transmission, the conventional type, but it also provides better fuel economy, better controllability, and quieter machine operation for the operators. And then our really big machine in the family is the 944K wheel loader. This is a machine that when you stand next to the tire is taller than you. It's a very large piece of equipment. And our customers really enjoy the additional controllability that they get with the electric drivetrain, just because the separate motors for each wheel, as you see in the diagram on the lower right, allows excellent traction control compared to a conventional differential that you'd see on a mechanical drivetrain. Also, the key topic of this presentation is long-term reliability. And I'll talk a little bit about how using these electric machines to drive the wheels and generate the electricity for the drivetrain helps us guarantee long-term reliability of these vehicles. So just as a quick glance, we've got millions of hours already in the field on collectively across the machine population on these 644 and 944 hybrid diesel electric wheel loaders. So we've already been able to prove that this is a reliable machine that stands the test of time. But what I'll be talking about today is sort of some of the steps of how we ensure during the design process that reliability goal will be met. A couple other products, getting away from the diesel electric vehicles, we've actually got some full battery electric vehicles that have been released. This electric backhoe is something that we've sort of joint tested with a utility company called National Grid. It's a fully electric backhoe loader, so it's got a loader bucket on the front and a backhoe boom on the back. This machine would really shine in urban environments where the noise and exhaust emissions would be a problem, especially working late hours of the night with the noise issue, and even allowing operation inside of buildings because there's no exhaust to worry about. Secondly, here we've got this battery electric excavator, which was just unveiled at CES this January. It was also on display at the Con Expo in Las Vegas, and I think it was last month. So among those, those two machines were displayed among several others. Actually, at Con Expo, we showed off 7 new electric and hybrid electric construction machines. So with a backhoe and the excavator that I mentioned, we've got a couple different sizes of loaders shown at the bottom, as well as a diesel electric crawler, so a bulldozer. So it's an exciting time to be working in the area of electric drives in the construction industry. Now that we have talked a little bit about what John Deere is and what our involvement is in producing electric drive vehicles where reliability is a key requirement, I'm going to get into a little bit more of the technical details about how we ensure that we meet vehicle reliability goals by starting at the component level. And specifically, I'm going to talk about electric machines. So that would be your motors and generators, because that's the component that I'm most involved in my role. So just a brief introduction to reliability. You basically start with the reliability goal for the overall vehicle. And the vehicle is made up of many subcomponents. So you've got your engine, your hydraulics, your e-drive components. All the reliabilities of those separate subcomponents have to be compiled together to result in a life prediction for the vehicle itself. So within each subcomponent, for instance, e-drives, the area that I work in, we've got multiple subcomponents within those. So cables, inverters, controls, and electric machines, among many other parts. So in order to meet the overall vehicle's life goal, the component life expectations have to be much higher, because you have to consider the fact that you're essentially statistically combining the reliabilities of all the separate components into the composite life of the machine. So in summary, in my role, we have to design our electric machines, so our motors and generators, to be extremely reliable and maintenance free while remaining cost sensitive in the design. So a little bit more about concerns for balancing reliability and cost. Of course, you could design some sort of ideal electric machine that used, crazy materials to be reliable forever. And the 944K wheel loader was John Deere's first entry into the electrification area, as well as its first entry into this size class of four-wheel drive loaders, so sort of the mining class of loaders. As a result, since we didn't previously have experience with that sort of a machine, there was limited information available about how our customers would use that machine at the time. So as you can see in the plot on the right, if we look at something like motor winding temperatures from our field history data that we have now, in hindsight, the motors are running quite a bit cooler than maybe they could. So maybe these motors have a little more capability than they need for the application. So now with millions of hours of customer field data to work with for future designs, it allows much more robust inputs to our reliability calculations for future e-machines, and allows us to design the motors more right-sized for the application. So just a little bit of a crash course on a basic component reliability concept. This is what you might have seen, what they call the bathtub curve for component failures. So at the left-hand side, you've got a higher rate of failures, which is near the beginning of the life of the component. This would be failures due to things like manufacturing defects or quality issues. Then you've got the design life of the component, where typically failures are minimal. If it makes it past that initial quality stage, then failures are minimal for most of the design life. And then as the component exceeds its design life, then you start to get an increasing number of failures, again due to just simply wearing out of the component. So the first part of this curve, the early failures, are typically something we detect at John Deere by doing vehicle testing, which is sometimes very aggressive testing of the vehicle, as well as component level testing. So in the case of our motors and generators, we'll place them on a test stand like a dynamometer and actually make them work against each other and test their limits, essentially, to see which potential quality issues would surface during that type of an aggressive test. This helps us cover the understanding of the first part of the curve. The later failures after the design life is something that we also want to be able to predict, because we want to make sure that the component that we select is going to fulfill the intended design life of the vehicle, like I mentioned before. So the way that we do, the way that we analyze whether a component will meet those goals is through things like accelerated life testing methods, which is something that I'm going to focus in on in the future slides here. All right. So like I mentioned, I'm going to be focusing on the electric machine subcomponent of the electric drive system in our electrified construction and forestry vehicles. It looks like my labels got a little shifted there, but the electric machine is comprised of many different components. You've got windings, magnets, mechanical parts like the shaft, the bearings, the splines, many different things that you could conceive as a failure mode in an electric motor. But when it really comes down to it, the key things that really drive the life of electric machines, at least in this size class of electric machines, are really the bearings and the stator windings. So the lifespan of a ball bearing is primarily driven by the speed that it operates at, the amount of time it spends at each speed. Sometimes it can be driven by the torque that the motor is delivering, especially in the case of driving into a gear train where you're applying side load to the bearings. It has to do with vibration. So if the machine is in a very high vibration environment, it can cause damage to the bearings, and lubrication. As far as the windings go, they're a little more of a complex thing to predict. The failure mode of the windings is essentially insulation breakdown. And the big drivers for insulation breakdown are the temperature, the amount of time spent at each temperature, the voltage stresses that are applied across the windings, and potentials for chemical exposure of the windings, because the windings are insulated with various types of varnish and other chemicals. And if there's an incompatibility with say a lubricant or a coolant that's used in the motor, then you might have damage to the winding insulation. So I've discussed what the failure modes are and what the primary lifespan drivers for e-machines is, so the bearings and windings. Now I'll talk a little bit about what we do to analyze and predict the life of these subcomponents. So for bearings, bearing suppliers, since ball bearings are a long time tested technology, the bearing suppliers tend to have very extensive and accurate tools to predict lifespan, because they've had decades of experience perfecting these tools as the technology of ball bearings developed. We typically rely on the bearing suppliers to provide us calculations of lifespan by providing them with speed profiles and lubrication details, as well as other inputs like vibration and G loading and things like that. The windings, unfortunately, are far less straightforward. There's such a crazy variety of insulation materials and insulation systems. So how the insulation is placed into the slots of the motor. And there's constantly new technologies coming up in the area of windings. Also, unlike the bearings where we can sort of predict the stresses that they're going to get by looking at drive cycle data, the stresses to the windings tend to be very application specific. So for this presentation, we're going to be focusing mainly on prediction of winding life as opposed to both bearings and windings, but we'll tie them both together at the end. So as I mentioned, there's several factors influencing winding life, and I'll kind of get into a little more detail about those here. So I discussed voltage stresses, chemical exposure, and temperature. The voltage stresses are sort of something that we can control or predict through the design of our inverter drive system that controls the motor and regulates the current going into the motor. So that's a little bit lower risk because it's something we can measure, and it's something that's fairly consistent from one vehicle to another and one application to another. We can also control chemical exposure by selecting the correct fluids for cooling the motors, or preventing exposure to chemicals altogether through the use of environmental seals and shaft seals and things like that. Unlike the other two, temperature is very load dependent. So the temperature of the windings is going to change constantly depending on a changing torque cycle that the machine is, the motor or generator is delivering. So it really depends on how the customer uses the machine. Not only that though, but also the surroundings and ambient temperature, how well the cooling system of the vehicle is working. Say if radiators are getting plugged up in a dirty environment, all these factors affect the winding temperature. So it's a lot harder for us to control, and sometimes it can be harder for us to predict. But we need to understand how how to estimate what this winding temperature will be over the life of the vehicle, so that we can predict how many hours of life we will get out of this motor or generator. So I've told you what we need to get. Essentially, we need to know how many hours this motor is going to spend at each, or what percentage of its life it's going to spend at each temperature over the course of the life of the vehicle. But what information is really available to us to make these predictions? One of the main ones is field data from machines on customer sites or from machines that we have at our own testing facilities. So we can look at torque speed history throughout an operation that we know that the customer will be performing. So something like loading a truck or digging a hole in the ground or making a pile with a loader. We know what sorts of operations the customers use these machines for the most part, and we're able to record data that represents these operations. So obviously it becomes important here to make the operations during our tests as realistic as possible. So we have very skilled operators that their purpose is to do these operations in a way that's representative of how a customer would. So from that torque speed data, ultimately we would love to know what the e-machine temperature would be at every torque and speed combination available. But clearly that would require an incredible amount of testing in the lab. So what we typically do, and we find it to be more than adequate in accuracy, is to bin the torque and speed points into sort of groups that allow us to test a more reasonable amount of points in the lab. And what we essentially do is, once we have our torque and speed bin sizes defined, we can sum up the amount of percent life that lies within each of those bins. We can run a test point within each bin in the lab to gather the stabilization temperature of the motor at that torque and speed point. And then once we have the percent time at each temperature, we can feed it into our reliability calculations. So that gives us one piece of the puzzle. That gives us how is this motor going to be used in the application. So what temperatures are the windings going to be for what percentage of the vehicle's life? But that's only really half the equation. We also need to know how long will a motor last if it's at a certain temperature for its life. So that essentially comes from accelerated life testing, because the winding life predictions for a motor could be hundreds of thousands or even millions of hours. So if you tried to test to a failure at normal operating temperatures, it would take far too long. There would be no practical way to do that. So since the key driver that we're trying to analyze for electric machine reliability is the temperature of the windings, we can accelerate the failure of a motor by running it at a temperature that far exceeds the normal operating temperature. So once we gather enough failures from enough different samples at various temperatures, it allows us to sort of build a model for how long the electric machine would be expected to last when more normal temperatures are experienced. And although I'm not an expert myself in that particular aspect of the calculations, what I really wanted to convey here is how we obtain the inputs that go into that, so that our reliability engineers who are experts in that field can make those life predictions accurately. So just to sort of summarize the overall process here, the goal essentially is at the far right. We want to know the electric machine life prediction. So how many hours is this electric motor gonna last if the customer operates it in this particular set of different operations for a known percentage of its life. And obviously this then gets combined into subsystems like the drivetrain and then eventually to the overall vehicle. As I discussed, typically we provide speed profiles and other inputs to a bearing supplier to get a prediction for the bearings themselves. We take our accelerated life test data as well as our assessment of what temperatures the machine is going to operate at over the course of its life. That comes from our our block operating points and testing in the lab. And then our reliability engineers will use software tools like ReliaSoft to extrapolate that to a winding life prediction in hours. And typically, I sort of indicated it by the number of number signs there, but typically these bearing and winding individual life predictions are very high. And then when you combine them, as you continue to combine the life predictions for the components and subsystems, it boils down to the overall life goal for the vehicle as a whole. So that essentially is the part of the process of life prediction that I'm involved in with my role at John Deere's Electric Drives Group, as I help guide what tests we put these motors through. And I have to use input from customer field data as well as testing at our own John Deere proving grounds as my source of data to guide what those tests should be. So I believe that is the end of my slides. And at this point, I'd like to open it up to questions through the chat there. So thank you very much for listening.
This has been super fascinating. I'm like, Skylar, I was thinking about these big trucks that I know other people I've talked to, they say the coolest part is that when you get to work for Deere, you have an internship, you get to go and like play on the big trucks.
Absolutely, yeah, that was
if you're just doing some design work.
Highlight.
Here, I mean, this was really interesting questions. What about, can you create a custom chat GPT for motor design?
Let me.
Did you see that one? Here you go. Thanks, Sylvie, for pushing that over.
Can you create a custom chat GPT for motor design? It's already being done. I honestly am not familiar with that term.
Oh, okay. That's interesting, right? So, well, I guess there's being one done for drug development. So,
okay, I guess I got to research that.
Yeah, so we'll send that over. So, the other one was interesting. Have there been any unexpected, surprising outcomes or consequences as Deere has moved toward electric machine options for customers or consumers?
I think there's always new ways that we hear from customers that they would see using an electric vehicle, and I guess advantages that our customers point out about electric vehicles that we wouldn't have expected. Like for instance, we might have predicted that an electric backhoe would allow you to operate inside of a building because there's no exhaust emissions, but there might be some other niche application that really makes sense when you actually see it, but we wouldn't have been able to predict that from the start.
That's really interesting, because I thought the inside was in the noise factor, right? Because again, when you live in an urban environment, or even you live maybe out in the suburbs, you don't want noise past different hours. So I think that was a really interesting piece that you brought up about the noise factor of construction, because if you lived in a city, that noise can be overwhelming.
Yep. And initially we might have just thought of the noise as an annoyance factor and noise pollution, but something else that kind of comes from when you actually get in one of these machines and operate it is that you notice things like say you've got a worker out on the ground observing where you're digging, down in a trench to look for a pipeline or something, and you're up in the machine operating it. If you have the windows open, you can hear them talking to you because the machine is so quiet that you can have a conversation with them. So that not only increases sort of the awareness of the construction site, but also
I think for lots of safety reasons, right? If something's happening, you can hear it happening, not that loud, engine noise.
So yeah, even just the efficiency of getting things done improves through
Right.
that.
And I think maybe even the time that you can work, right? The time that you might be able to work because of the noise factor. There's
Yep.
noise ordinances when you're working in certain environments, right? So that's when
Yep.
and
So
that
in
whole,
response, yeah, there's plenty of unexpected, surprising outcomes. It's hard for me to come up with some more on the spot, but it's definitely an
well,
exciting place to be working.
we think about you think about the forestry aspect, and maybe there's not a lot of people out there, in the forestry aspect of it. We think about on the farm, and those kinds of what you'd expect there. But I think thinking about the construction business of it, because again, I was really impressed with the number of vehicles and the sizes. I was sitting there thinking, what would be my favorite one to play with? I mean, look at this,
Yep.
when you mentioned the tires, I'm sure twice my size. That would be really great.
Yep.
This was a really interesting question. The right to repair statutes and design efforts. Has this when customers come up, the implications of that? And
I don't really know much about that
about
side
that?
of things from my position as a design engineer. I imagine if you ask that to one of our customer support engineers or a customer service type engineer, they might have a better answer. But as far as my work at the component level with electric machines and power electronics, I haven't really had discussions about that. So yeah, sorry, I'd have to defer that question to an expert.
That's always a good thing. So this was interesting. What happens when a failure mode in the field is different than the failure mode in your accelerated testing?
Well, that can certainly happen. Yeah, we know what our most common failure modes are, but it's always amazing what customers will find to do with the machine that we would never have expected, or just environments that the machine might be having to operate in that are far worse than what we would hope that they would have used it for. So for instance, if a machine gets flooded with water or something like that, and there's water above the electric drive components, and it has enough time to make its way in through a vent or something like that, that might cause a failure that we wouldn't predict from our typical assumptions of thermal being the main driver for failure. So absolutely, yeah, there's ways that could happen. Or if somebody's just using the machine for some sort of aggressive operation that exceeds the ratings, maybe within the capability, but exceeding the ratings, so it can do it, but it shouldn't.
Well, I thought that part that you also brought up about the temperature of the components was really interesting. So again, that is another benefit that you found that, maybe you weren't expecting at the onset, but really a nice benefit of the temperature of the components and how the stress that puts on, especially in the extreme environments that you could be working in.
Yep, high temperature and high debris environments, because it causes the efficiency of the cooling system to decrease. And obviously, the machines have systems in place to help combat that debris. Like reversing the fans to blow the debris out of the radiator, for instance. But there's all these instances where it's beyond the capability of those systems just because it's an extreme environment. So.
Well, you build in an extreme environment. Iowa has some real cold weather too.
Yep. Yeah, we've got a pretty wide swing here.
We've got a pretty wide swing of things like
it helps us for testing, honestly.
Interesting.
Good to be able to test in the cold winter and the warmer parts of the year too.
So I know Deere does a lot, because I know you've hired a lot of interns from Atacapanu, and you've hired a lot of young people right out of school from Atacapanu. But what advice do you have for students interested in these kinds of careers that you've had, or the kind of cycles you have available at Deere and things like that? I think might be some interesting things for you to talk about here in terms of those opportunities.
I don't know if you're going to have a way to provide my contact info, but I'm open to conversations with anyone that's interested in doing say an internship or a part-time student type arrangement. Deere really enjoys having part-time students that work in as they have time to during the school year. A lot of those positions are fully remote, so wherever the student's going to school, they can just do some work for John Deere as they get the chance. And then in the summertime, they'd likely be welcome, to do an internship. So I certainly would like to get as many applicants to those types of positions as possible. So feel free to contact me directly if.
I'll make sure I'll pass that on. And I know, and I've always passed on. So Deere does have a booth during this event. There is an expo area, and John Deere has a booth, so you can register your interest or hopefully meet with some people. Some of your wonderful recruiters usually join us for our events. I know at our conference in person last year in our student leadership conference in North Carolina, I know Deere hired about 11 people off of the conference floor. So that was really great. So, and we've been at our different schools right around the area, the different chapters that we have right around the area. We have a great partnership with John Deere. So if you are interested in those kind of careers, I'm certainly happy. If you're listening to this, I'm happy to hook you up through HKN and we can get you over to Deere, no problem.
Yeah, and I'm not, I'm not in HR or anything. But I know who to talk to, and I'd certainly be very happy to help. Put you in contact with the right people if you're interested.
Thanks. So I found that really, we found that very strongly to be this duration with Deere is that your engineers have been always happy to reach out and advise young people and students and even young engineers about these kinds of opportunities that they might not have thought about. Because really, how cool is that? That you get to build systems on these amazing vehicles, right? They're just over the top interesting.
Yeah, I highly recommend an internship, for instance. That was my experience prior to starting full-time. And not only is it something that obviously led to my full-time job now, but it's also just a very interesting and fun experience. Like Nancy mentioned with the getting to operate these giant machines. I grew up kind of around farming and was able to luckily drive tractors and things when I was younger, but for a lot of the students, that's their first time driving something bigger than a car and something that could lift a car up in the air and drop it if you wanted to. It's a very large machine. So
yeah, actually, one of the people attending had mentioned that her father-in-law is a farmer.
I saw that. Yeah, that's very interesting.
Really, and she's got to drive a lot of those. Yeah,
I was just going to comment on that. So that's very cool. They had a 250 kilowatt to 1 megawatt power range. That's kind of at the upper boundary probably of what we'd be working with a lot of our machinery, but who knows in the future as we, have the chance to move towards bigger and better projects, we could be moving into that regime too. So we'll see where time takes us, but that's very cool story.
Yeah, I know. I've spoken to a lot of engineers who said, wow, this was the most fun thing. Or some of our interns have gone there that said they actually got to go out in the field and test and be on some of these vehicles. So not just sitting in a lab, but actually going out in the field lab and doing that. And there's another really good question here about, do you find the school prepared you for this need to prioritize the environmental concerns of today and working in electric machines?
Let me take a look at that.
Did you find school prepared? Oh, here we go. So thanks, Sylvie, for passing that over.
Yeah, I guess I didn't specialize in that area of when I was in school. I was completely in the technical side of things. I feel like my schooling definitely prepared me for the thought processes that go into researching the new technologies and how to do effective scientific method in testing things in the lab and things like that I do at John Deere regularly. As far as the environmental concerns, I'm aware that there's, environmental benefits to, the immediate emissions elimination of using a battery electric vehicle. And, but yeah, I didn't really study that in school, honestly. I really focused on the technical aspects and the science. So,
well, we at Excavator, I get to talk to a lot of young people currently in college and currently early in their careers. And this is a big concern. So I think it's great to be able to have the opportunity to work for a company and on a technology that really is addressing a lot of these issues in terms of climate and environmental concerns. So I think that probably is another nice aspect of your job, maybe an unattended aspect and a nice aspect of what you get to do working for a socially responsible company like you do.
Okay. Yep. I agree.
Yeah, so that's great. So there's other things that I put in there. So I really want to thank you, Skylar, for being with us today. I want to thank John Deere for sponsoring this for this session. We will have, John Deere does have a booth during this conference. And like you said, if you're watching this and you do want to connect with John Deere, certainly you can reach out to HKN at info@hkn.org, and we'll be happy to connect you over. Anybody who registered for this conference is on our resume book, which you're going to get a copy of, Skylar. So that's always a nice advantage to have. So
yeah, I'm looking forward to that.
Yeah, so HKN TechX continues throughout today and all day tomorrow. It's a total of 10 sessions that we have. This will be on demand if you missed it or you missed any part of it and you want to watch it again. It'll be on demand on the platform. And we really appreciate this opportunity to bring you the speakers and information, technologies, and companies that are really working in these exciting areas, emerging technologies. I invite you to join us. Our next session coming up is on the CHIPS Act, which is very exciting, right? This new CHIPS Act that was passed by Congress and is being implemented here in the U.S. is going to have a lot of implications for technology companies, and technologists in terms of jobs, opportunities, where these companies and what's happening in these areas. So that's going to be at 12:15, and we invite you to join us for that very shortly. And later, the recruitment fair, drop by and see our friends from John Deere, talk to them about the opportunities they have open for both internships, recent graduates, and for career professionals. Thanks so much, and we'll see you around TechX.
Yeah, thank you very much.